Hi everyone, I hope this finds you well. In this lesson we're going to be talking about FM synthesis. This is going to be the last big lesson where we present a lot of new material. The last couple lessons will just be going over how to complete the final projects and offering a few additional skills to empower you guys to do that with a little more performativity. But in today's lesson we're going to be talking about FM synthesis. We're going to start with a quick review of some important ideas like harmonicity and audio rate modulation. And then we'll spend the rest of the lesson talking about FM synthesis itself, talking about theory and patching, going over what algorithms are and trying out some different algorithms, talking about the history of FM synthesis, spending some time talking about the Yamaha DX7 synthesizer, and then we'll end by looking at a really powerful module, really a really powerful synthesizer in its own right, Valley's Dexter module. So before we start any of that, let's quickly review what we were talking about last time. Last time we looked at this list of all these different types of sound synthesis. This is not an exhaustive list, but this is some of the most common. We already know subtractive and wave shaping, the East Coast, West Coast models. We talked about granular synthesis last time. I was hoping today to talk about additive synthesis and FM synthesis, but FM is a pretty big subject, so it makes sense to really just focus in on that for today. But I'll post a video on additive synthesis on Blackboard if you're interested in checking out how to do that in VCB Rack. In addition, we're not going to talk about wavetable synthesis today, but one of the modules we'll look at, the Dexter module, does wavetable synthesis. So I'll post another video on Blackboard going over what wavetable synthesis is and how it works, so you have a better idea of that if you want to start exploring that in Dexter as well. So let's start with a review of the idea of harmonicity. So this is an idea that's really important to FM synthesis, and it's something we're all familiar with already, but it doesn't hurt to go over it again. So harmonicity has to do with how harmonic a sound is. So of course we've got these two different categories, harmonic sounds and inharmonic sounds. In harmonic sounds, all the harmonics, all the overtones, all the partials are integer multiples of the same fundamental frequency, and as a result, the sound is going to cohere into a single coherent pitch. So for instance, a harmonic overtone series might be 100, 200, 300, 400, 500, 600. 100 is our fundamental frequency, and then all the overtones are integer multiples of that. 2 times that, 3 times that, 4 times that, etc. And this is the kind of harmonic spectrum we have in triangle waves, sawtooth waves, pulse waves, things like that. A sine wave doesn't have any overtones, but because it's just a fundamental, it's still a harmonic sound. Then we've got inharmonic sounds, where the overtones are not integer multiples of the same fundamental, and as a result, the sound doesn't fuse together in our perception in the same way. So an inharmonic overtone series might be something like 100, 216, 337, 459. This series of numbers is not integer multiples of that fundamental. These are all off by a fair amount. So we end up with a sound that's going to sound kind of bell-like, a little more inharmonic, and the sound's not going to fuse together into a single pitch in our perception. We might have really, really inharmonic sounds like noise, like white noise, pink noise, blue noise. Those are all highly inharmonic sounds. And then we've also talked about, like on the MS-20 with ring modulation, we can get sounds that are not quite as inharmonic as noise, but that are still inharmonic enough that they don't cohere into a single pitch. So now let's review modulation. I know we're all familiar with this, but some of the ideas and terminology here will be important for our discussion of FM. So in modulation, we're using one electronic signal to modify another, and modulation typically requires at least 2 signals. One's called the carrier, and one's called the modulator. The carrier is the audio signal that's being modulated. This is usually coming from our VCO, so the signal that comes out of our VCO that's somehow being changed by some other wave. That's called the carrier, and that other wave that's doing the changing, that's doing the modulating, is conveniently called the modulator. So this is the signal that's modulating or changing the carrier. And this very often comes from an LFO. So to really solidify this review, let's talk again about amplitude modulation. We've talked about this before. Amplitude modulation is what we have when the modulator is changing the amplitude or the volume, the loudness of the carrier. And when this happens at sub-audio rates, when our LFO is moving at 20 hertz or less, this is going to produce a tremolo effect. Okay, so here we are in rack, and I've got some amplitude modulation happening. So I have a VCO here in the middle. The signal from that VCO is running through a VCA, and the output of that VCA is running through an analyzer, a spectrum analyzer here, and then into my mixer. And then this VCA is being modulated by this LFO, and we can see this LFO in the scope. It's a unipolar LFO, so it's only moving in positive voltages, and that's because we can't get any quieter than 0 volts in our loudness here, so it doesn't make sense to have a bipolar LFO here. So you can see as the LFO rises and falls, the volume of our, in this case, sine wave changes. And as we change the rate of the LFO, that tremolo gets faster and faster, or slower. All right, so that's sub-audio amplitude modulation. But if we increase this LFO so it gets faster and faster and eventually starts moving into audio frequencies, frequencies over 20 hertz, we'll see that we start to get what's called ring modulation, where we get these sidebands. So if you focus on this center frequency here, which is 880 hertz, you'll start to see these sum and difference tones break off. And so now I've got a sum tone above my carrier and then a difference tone below. And that's the sum and the difference of my LFO's frequency and my carrier's frequency. And so the higher I go, the sum tone gets higher, the difference tone gets lower. Now my LFO can only get so high, only goes up to 1000 hertz. So what I'm going to do now is mute this and then come up here where I've got the same patch, except this time, instead of using an LFO to do my modulation, I'm using a VCO. So, and I've also run my VCO through an attenuverter with an offset because my LFO down here, as you can see, it was unipolar, but VCOs are bipolar. So in order to get my VCO to be unipolar, I have to offset it by 5 volts. So I've got my VCO, it's offset by 5 volts, and then that is modulating the amplitude of my carrier VCO. And so now as I move this up and down, you can see those sum and difference tones moving all over the place. Now you notice something weird happens right around here. My difference tone gets lower and lower and lower, but then when it gets all the way to 0 volts, it turns around and starts coming back. And the reason for this is that in the frequency world, there's not really any audible difference between negative frequencies and positive frequencies. So what happens is our difference tone is actually going to get lower and lower and lower until it starts moving in the negative territory. But because, say, negative 100 volts and positive 100 volts sound the same, they don't actually make any difference in the audio frequency world, on our spectrogram, we'll just see that when it goes negative, it's just going to turn around and come back. And so the negative voltages are turned into positive voltages. Let's take a look at that. It was in the negative voltages, and it turns around and comes back. And now both our sum and difference tones are moving upwards higher and higher and higher. And this idea of negative and positive voltages being equivalent is going to come back later. Now, one little side detail here is that technically in true ring modulation, we don't even hear the carrier. We suppress the carrier and we just get the sidebands. So over here, I've got a sequential switch that I can use to bypass this little filter here. So right now I'm just going out my VCA through this switch and then down to my mixer. But I can also switch over, take a detour and go through this filter and then go out. And I'm just going to use this filter. It's a band reject filter, and I just have it set to bypass my carrier to filter out just that carrier frequency. So here's with the carrier, and here's without. And so now as I change, I just get my sidebands, and I'm not hearing that carrier frequency any longer, which is true ring modulation. Now we're just doing this with sine waves, so they don't have any overtones. So we just have one sum tone and one difference tone. But if we were to do this with, say, triangle waves or something, we would end up with lots and lots of harmonics, and we get the sum and difference of every harmonic in that spectrum, and we end up with much richer spectrums. These are like the ones that we heard on the MS-20. Actually, the ones in the MS-20 use pulse waves, so there was even more harmonics. All right, so now let's quickly review frequency modulation. I know you guys are all familiar with this. In frequency modulation, instead of the modulator changing the amplitude or the volume of the carrier, the modulator is changing the frequency or pitch of the carrier, and this is going to yield a vibrato effect. All right, so here I am in Rack, and I've got a VCO. I'm using the Bog Audio VCO, and I'll explain why in a sec. And the sine wave output from that VCO is going through a scope, through a spectrum analyzer, and out my mixer. Then I've got an LFO, and the sine wave output from that LFO is going into the FM input on that VCO, and it's also going into my scope as well. So now, as I bring up that FM knob on my VCO, we can start to hear that vibrato taking place. And so we can see on the scope that as my LFO is up at a higher voltage, it brings the pitch of my VCO up. As it's down at a lower voltage, it brings the pitch of my VCO down. And this gives us our vibrato effect. Now the polarity of my VCO makes a difference. Right now it's unipolar, so it's only moving in the positive voltage. So it only brings the pitch of my VCO up. So right now my lowest pitch is 440 hertz here. And as I bring up the FM, that unipolar LFO is bringing my pitch up above and then back down to 440. If I were to switch to a bipolar LFO, now my LFO is moving through negative volts to positive 5. And as I bring up that FM, it's taking my pitch above 440 and then also below 440. So 440 becomes a center frequency. It's no longer the bottom frequency. And of course, the frequency of my LFO changes the rate of that vibrato. And the amplitude of that LFO, which we determine with this FM knob, is going to affect the width or the depth of that vibrato. So here it's relatively narrow. As we bring that up, it gets wider and wider and wider. And you'll see that as we increase the speed of this LFO and we start to move into audio rates above 20 hertz, we start to generate a lot of sidebands. And we're using just sine waves here. And even with just 2 sine waves, we've generated more than just the sum and a difference tone, but a whole lot of additional sidebands. So we're going to talk more about these sidebands here in just a second, but first let's talk about why I'm using this Bog Audio VCO. So this is a quick little technical detour. This stuff is important because it can cause confusion if you guys don't know this and you're working with different VCOs and getting different results and you're not sure why. So I'm just going to go over this really quick and I'll provide a link with more info if you're interested or want to know more about this. But basically there are 3 types of FM inputs: exponential, linear, and linear through 0. And there are important differences between each of these. Exponential FM inputs use a volts per octave format. This is why, for instance, in the VCV fundamental VCOs, you can send a volts per octave input into the FM input and then just crank it all the way up, and then your FM input acts like a volts per octave input. And that's because this FM input uses a volts per octave format. And the result of that is you get a wider range. You can use really, really wide vibratos. The problem is that in doing that, the center frequency doesn't really stay in tune. When you have a really wide vibrato, what feels like the center frequency isn't actually the pitch you're playing on your keyboard, for instance. A linear FM input uses a different format. It's something called hertz per volt. And in this case, the center frequency stays in tune better. However, it can't produce negative frequencies. So in the way that we saw in ring modulation, when that difference tone went into the negative range, it actually just turned around and came back. With linear FM formats, that doesn't happen and things just bottom out at 0. And so that can make your center frequency sound like it goes out of tune as well. This is the kind of format you have on the Bufaco even VCO. Linear through 0, however, uses a hertz per volt format also, but this time the center frequency stays perfectly in tune because this time it allows negative voltage as well. So if you have a sideband that goes into the negative territory, it turns around and comes back and we hear it in the positive range as well. So this is the best for working with FM. It's what we have on the Bog Audio VCO, and that's why I'm using that today. It's kind of tough to do in the analog world, so you don't actually find this on very many analog VCOs, but it's really easy to do in the digital world, so that's why we have it on the Bog Audio VCO, and you'll have this on a lot of digital FM synthesizers as well. So you'll notice on that Bog Audio VCO, there's a little switch next to the FM knob that switches between exponential and linear. And when it's in linear mode, it's actually linear through 0. So that's going to be really useful for us as we're doing FM. All right, so now let's talk a little bit more about audio rate FM. When we're doing FM with audio rate modulators, we can produce lots of sidebands. And as you saw, even with sine waves, we can generate tons and tons of sidebands. So because FM produces so many sidebands, a lot more than we had in ring modulation, it's common to do FM with only sine waves. And so that's what I'll be doing today. You guys can definitely try it out with sawtooth waves and triangle waves and things like that. You'll get some interesting results, but it generates a lot of harmonics and you'll find yourself into noisy territory pretty fast. So one important idea when we're talking about FM sidebands is the harmonicity ratio. So if the ratio between the carrier's frequency and the modulator's frequency consists of integers, that is like a 1-1 ratio, a 1-2 ratio, a 1-3 ratio, etc., the resulting sidebands are going to be harmonic. And the FM tone that you end up with is going to be a harmonic sound. And if the ratio between the carrier and the modulator's frequencies is irrational, that is, they're not integer multiples of each other, it's like 1 to 1.5, 1 to 2.2, the resulting sidebands will be inharmonic. All right, so let's take a look at this idea of harmonicity in rack. So I've got two Bog Audio VCOs here, one's modulating the other, and I've set them both to linear FM. And right now, this first one, my carrier, has a frequency of 100 hertz, and my modulator has a frequency of 200 hertz. So this is a 1-to-2 ratio, so this is going to produce a harmonic sound. So as I increase my FM, we have all these harmonics show up, these side bands, and this produces a harmonic sound, and I can go ahead and play a melody. And notice I've got my MIDI CV input here, and I've got the same volts per octave signal going to both my modulator and my carrier. And that's because as one of these moves, I want the other one to move in the same way. I want to preserve that ratio between them, so I need them to move together. If they don't move together, then that ratio is not going to be preserved. And you get these really dissonant sounds as one moves and the other one doesn't. So I want them to move together. And that produces a nice harmonic sound. Let's try an inharmonic ratio. I'm going to leave this carrier at 100, and we'll set the modulator to, instead of 200, 245. And so now this is a 1 to 2.45 ratio, so this is going to produce inharmonic sidebands. And sure enough, as we increase this FM, we hear all these inharmonic sidebands show up. That doesn't sound bad, it actually sounds kind of amazing. But it just means that these pitches are not going to cohere together and form a single coherent pitch. And we get this dark, dissonant bell-like sound. So let's talk a little bit more about these sidebands. In ring modulation, we calculated the frequencies of the sidebands by just finding the sum and the difference of our carrier and modulator's fundamental, and if there's overtones, the overtones as well. It's similar in FM, but we generate a lot more sidebands. So there's a simple formula to calculate what the sidebands are going to be, and that is Fs equals Fc plus or minus n times Fm. Okay, that might not have sounded simple, but if you look at what each of these variables means, it's actually pretty clear. Fs is going to be the frequency of the sideband. So to calculate that, we're going to take Fc, the frequency of the carrier, and then add and subtract it from the frequency of the modulator times n, which is the order of the sideband, basically the number of the sideband. We can have any number of sidebands as we increase our modulation index. So we're just going to go up through the integers there. So let's look at an example. If our carrier is 100 hertz and our modulator is 200 hertz, we have a 1 to 2 ratio. It's going to be a harmonic sound. We know that already. Then we can calculate the sidebands. Let's start with sideband order 1. We're going to take the frequency of our carrier, 100, plus and minus 1 sideband order times 200, our modulator's frequency. So that's going to be 1 plus or minus 200, because 1 times 200 is 200. And so 1 plus 200 is 300. So our higher sideband is going to be 300 hertz. 1 minus 200 is negative 100. But remember, we're only working with absolute value here. So that's just going to be positive 100. So our first sidebands are going to be 300 and 100. All right, let's find our next two. 100 plus or minus 2 times 200, which is 100 plus or minus 400. Well, 100 plus 400 is 500. 100 minus 400 is negative 300, but for our purposes, that's just 300. And then the next one, 100 plus or minus 3 times 200 is 100 plus or minus 600, so that's going to be 700 and 500. And we would keep going. We could do sideband order 4, sideband order 5, 6, 7, 8, 9, 10, etc. But you can already see right now we're getting harmonics of 100, 300, 500, 700. So this 1 to 2 ratio is only generating odd-numbered harmonics. So we'd end up with a timbre that's kind of in the same sound world as a triangle wave or a square wave. Now let's look at an inharmonic example. So if our carrier is still 100 hertz, this time our modulator is going to be 140 hertz. So this is a 1 to 1.4 ratio. So our sidebands are going to be, well, the first one is going to be 100 plus or minus 1 times 140. That's 100 plus or minus 140. And we get 240, and 100 minus 140 is negative 40. So again, that's just the absolute value, so that's 40. So our first group of sidebands is 240 and 40. Next group, 100 plus or minus 2 times 140 is 100 plus or minus 280. That gives us 380 and 180. And then the next group, 100 plus or minus 3 times 140 is 100 plus or minus 420, which gives us 520 and 320. And you can tell by looking at these numbers, 40, 240, 380, 180, etc., they're not part of a harmonic series. If 40 is now our fundamental, and a harmonic series built on 40 is not going to give us harmonics like 380 and 180. So we've got some harmonics that are outside of our normal harmonic series, which is going to give us a slightly inharmonic sound. Now you notice that we end up with a new fundamental. Our carrier was 100, but after the modulation, we end up with a fundamental of 40. In the previous example, our carrier was 100, our modulator was 200, and the lowest frequency was 100. So our carrier was still our fundamental frequency, which is useful if we're trying to tune a synthesizer and we want, for instance, when we press the C key on the keyboard to get a C. But here, in the inharmonic example, we end up with this new fundamental of 40 hertz, which is actually lower and which would be a little confusing when you press C on the keyboard and you end up getting a pitch that's lower than C. So one little rule of thumb that can help you remember this if you want your carrier frequency to stay the fundamental is that if the frequency of the modulator is greater than 2 times the frequency of the carrier will remain the sound's fundamental. So if the modulator is 2 times the carrier or higher, so if our carrier is 100, if our modulator frequency is 200 or higher, then our carrier will remain the sound's fundamental. So it's kind of a handy thing to keep in mind. So the next thing I want to talk about is modulation index, which is another really important idea with regard to FM synthesis. So modulation index has to do with just the fact that the modulator's amplitude, which we control with this FM knob, is going to determine the strength and the number of the sidebands. So the lower the modulator's amplitude, the lower our FM depth, the fewer sidebands we're going to have, and the lower their amplitude is going to be. And as we increase this FM depth, we get more and more sidebands, and they get louder and louder. And so in FM synthesis, increasing and decreasing the modulation index is often used instead of filtering a sound, because we don't need to filter to get rid of harmonics. We can just reduce the modulation index, and that reduces the strength and number of our sidebands. Or if we want more energy, we can just increase the modulation index. And we can also shape the modulation index with something like an envelope generator. So in the same way we do filter contouring with an envelope generator, we can do modulation index shaping with an envelope generator. So I'm going to go ahead and create an envelope generator. I'm going to add a VCA here. And before I send my modulator into my carrier, I'm going to run it through this VCA. And then I'm going to shape that VCA with an EG, and I'm going to just send a gate from my keyboard. And so now when I press a key on my keyboard, the modulation index is shaped by the envelope generator. So let's give myself some attack time, a little more decay, maybe a lower sustain and a little more release. And now I press a key. So we get these nice modulation index contours. Now, sometimes in FM, you'll hear people talking about modulation index as a specific number, as a specific ratio, but you rarely see that number when you're actually working with FM synthesizers, unlike the harmonicity ratio, which actually does come up a lot, as we'll see later. So I'm not going to go into how to calculate the modulation index right now. So the next thing I want to talk about is FM feedback. So here I've got a patch with just one VCO, just a carrier and no modulator. And actually, in FM, a VCO can act as its own modulator. We can send its own output into its own FM input. So I've got this VCO. Its output is running through a scope, an analyzer, and my mixer. And I'm just going to take this output, and I'm going to send it into its own FM input. And then as I increase the FM, I start to get this feedback. And at first I get this nice harmonic sound that actually sounds kind of like a sawtooth wave. And as we go higher and higher, we start to get this really noisy sound. Also, it's important that this is on linear mode when you do that, otherwise it'll start to bend and get out of tune. So this is referred to as feedback in FM synthesis. We generate a tone that has a 1-to-1 ratio because we're modulating a sound by itself, in this case, middle C by middle C. And as I mentioned, when we're at relatively low modulation indexes, we get a tone that's kind of like a sawtooth wave. You can even see that on the scope. It's starting to bend over and look like a sawtooth wave. And we get all these nice, rich, sawtoothy harmonics. But then at higher modulation indexes, we start to get this high-frequency noise, which eventually takes over the whole spectrum, which could be useful if you want to make a noisy sound, like a plucked string instrument or something that, with a nice envelope, can be an interesting shape. In fact, speaking of envelopes, let's go ahead and add an envelope to this. All right, so now I'm taking that modulation output from my VCO, sending it up into this VCA, and then out into my FM input. I've got my FM index up a little bit, my FM depth, and then I'm modulating that with this envelope generator, which the gate is coming from my keyboard. So now when I press a key, you can see during the attack, the decay, that modulation index is shaped, and it sounds honestly like we're just running a sawtooth through a filter with some filter contouring. And if we increase this depth a little bit, we'll get some noisy sounds in there as well, which might be useful if we maybe can get a plucked sound. So yeah, that's feedback in FM synthesis. Now we've done a couple things now where we've taken a VCO and we've added an ADSR and a VCA to kind of add some modulation shaping over time. And this is really, really common in FM. In fact, it's so common in FM that this little setup, a VCO with an envelope generator and a VCA, makes up a little microsystem called an operator. And very often in FM synthesis, we're working with multiple operators. That is, multiple VCOs that have their own envelope generators and VCAs already attached. And to make this idea of working with different FM operators easier, Bog Audio has this great FM op module, which is a small module that acts as a self-contained FM operator. So it's got one output. It's only sending sine waves because, as I said, in FM, we very often are only working with sine waves since that generates a lot of sidebands, all the sidebands we need. It features a built-in feedback loop. So if I unmute this, there's this feedback knob, which as I increase this, generates that sawtooth-esque overtone series. And if we push that, we get that noise. So we don't even have to reconnect the output to the FM input. It's just already internally wired that way. It's got a built-in envelope generator. You can see here, attack, decay, sustain, release controls, and a built-in amplifier. So we can send this envelope generator to the level of the sound. So if I check this little envelope button, the sound gets muted, and then when I press a key, let's go ahead and get something a little pluckier. We can map that envelope onto the level of our sound. We can also map that onto the feedback of our sound. So let me increase this feedback a little bit. We get that nice plucky sawtooth sound. It's also got this knob to increase the depth of the FM, but to do that we would need something going into this FM input. So let's go ahead and add another operator. I've got that here. So now I'm going to send the output of this operator into the FM input. And now when I bring up this depth, we start to get some FM as well. Now you notice this just sounds like the sawtoothy feedback, and that's because this is set to the same frequency ratio. So I'm going to go ahead and send my volts per octave up here, because remember we want the same volts per octave going to all of our operators. Also I'm going to send the same gate. And what's nice about the tuning knob on the FM operator is that rather than being in hertz or voltage, it's actually in frequency ratios. So we can actually just right-click and type in the harmonicity ratio we want, and that'll give us the corresponding sidebands. So right now I've got a ratio of 1 to 1. Let's say I want something like 2.5 to 1. So I'm going to set this operator to 2.5. This one down here is set to 1. So now when I increase the depth, I get this inharmonic 2.5 ratio spectrum. And let's go ahead and listen to that with the envelope shaping. This kind of weird plucky guitar-esque timbre. Now I can get this envelope shaping by turning the envelope on my depth here, or I can use the envelope on this FM operator and use the level output, and I'll get the same results. Actually, they sound ever so slightly different. But what's cool is we can give a different envelope to this operator. So let's say I want this one to fade in. So I get this plucky level down here, but the timbre up here can fade in. So it's kind of handy that each operator has its own envelope. So we've been doing a lot of work with a carrier and a modulator, but it's really common in FM synthesis to work with 3 or even more operators. So on the slide here, I've got 2 different layouts that use 3 operators. So on the left, I've got a setup where there are 2 operators modulating the carrier. And on the right, I've got a setup where there's a modulator modulating a carrier, and then there's a second modulator modulating that modulator. And each of these are going to sound different. Let's try them both out in rack. All right, so here we are in rack, and I've got my carrier operator down here. Its output is going to the scope, the analyzer, and the mixer. And then up here, I've got 2 operators that are both going to independently be modulating this operator. So this is like the schema on the left. So I've got the output of each of these operators going into a mu mix module, so I can mute each one of them, and then together their mixed output is going into the FM of this operator, and I've already got my depth up so that I can hear that, and I've already got the same volts per octave going to all of these operators and the same envelope gate going to all of these operators. So first let's take a listen just to my carrier. Just a sine wave right now. It's at a frequency ratio of 1. And now let's look at my first operator here. My first modulator is a frequency ratio of 0.5, which is actually going to be harmonic. It's an octave lower than my operator since 0.5 is half of 1. So this is still technically a 1 to 2 ratio. So if we unmute this one, we'll get a harmonic sound. Kind of a string instrument, plucked bass kind of sound. I've got a level envelope set here with a quick attack and a sustain of 0 and then a 3-second decay. All right, let's listen to my other modulator in isolation. So this one's got a frequency ratio of 4.7. So this is going to be an inharmonic sound. And I've got a level envelope set, this time with a slow attack. This time the attack is 3.3 seconds. So we'll hear the inharmonic spectrum fade in. So now let's listen to these together. So because this one's got a 3-second decay but a quick attack, and this one's got a slow 3-second attack, what we're actually going to hear is almost like a crossfade. As this modulator fades out, this modulator is going to fade in. So we're going to hear a harmonic sound that shifts to an inharmonic sound. So that's a really great sound that we can't get any other way than doing FM synthesis. Let's look at another example. So this is a setup like on the right side of the slide. So here I've got a carrier operator down at the bottom. I've got a modulator which is modulating that carrier. And then I've got another modulator which is modulating my modulator. So these are happening in a chain, in a cascade. And of course I've got the same gate going to all of them, and the same volts per octave going to all of them. So first let's hear just with the one modulator. So you can see my depth is up pretty high, so I get these really bright sounds. And I'm using the level envelope and the depth envelope on my carrier, and no envelope here on my modulator. All right, let's put our carrier aside and listen to our modulator that's being modulated by our second modulator. So we get this weird little plucky sound, and that's because this modulator has a really quick attack and a pretty quick decay, just 0 seconds and then 0.05 seconds on the decay. So we really only hear this modulator at the very beginning of the note. And of course, notice I've got the depth on my modulator here up a little bit, so we can hear that. So let's hear what happens when I modulate this modulator, and then I use this modulator to modulate my carrier. So we're going to hear all these together in a chain. So we get the same sound like that we heard before, except now we get this little noisy burst during the attack, which comes from this modulator. So that's how we can use two modulators in a cascade like that. So all these different arrangements of operators, of carriers and modulators in an FM patch, we call that an algorithm. And algorithms can consist of any number of operators. And there are 4 different kind of families of algorithms. And I've put them on the slide. All these examples use 3 operators. There's the stack or the cascade, which we just heard, where you've got a modulator modulating a modulator modulating a carrier. We can have algorithms that are like branches, where we've got 2 different modulators modulating the same carrier. We just saw an example of that as well. Then we can have a root algorithm, where we've got maybe one modulator modulating multiple different carriers. And then we might have even a setup where there is no modulator, where there's just a few carriers that are sitting side by side, and maybe one or more of them just has some FM feedback. Now notice I've indicated that some of those modulators in the other examples have the little feedback arrow, so any one of these modules can have feedback. It's common, however, for just one operator to be using feedback, and this was a precedent set by the DX7, which we'll talk about in a little bit. So that's why on this slide, in each of those algorithms, only one of those operators has feedback happening. So let's go ahead and try to set up some different algorithms using 4 operators. And we could do this by arranging these operators and disconnecting and reconnecting patch cords as we move through all these different configurations. But that could get kind of tedious, so this seems like a good opportunity to show you a cool family of objects called matrices. So a matrix is a module that allows multiple signals to be routed to multiple outputs through this grid-like array setup. So some matrices will have dials that allow you to scale voltage as it moves through it, Or they might just have mute buttons, little switches that allow voltage to either pass or not pass, acting like a gate or something. So Bog Audio has several matrix modules. I know it seems like Bog Audio Day. They've got a 4x4 matrix with dials that you can scale the voltage through. They've also got an 8x8 matrix. And then they've got a series of switch modules. So they've got a 4x4 set of switches, an 8x8 set of switches, and even a 16x16 set of switches. And these are useful for all sorts of things, not just for arranging FM algorithms. We'll probably look at these modules again before the semester is out as we talk about creating performative patches for the final projects. But for today, we're going to be using them to route some different FM algorithms. All right, so here I've got a patch where we're going to use the Bog Audio switch module to route some FM algorithms. So let's see what's happening in this patch. I'm going to zoom in a little bit here. So first, I've got 4 FM operators, and I've set them all to different frequency ratios. So this one's 0.5, 1, 2, and 2.5. I've also given them each different envelope shapes. So down here, I've taken the same volts per octave from my keyboard and sent that to every one of these operators. I've also sent the gate from my keyboard to each of these operators. And then the output from each of these FM operators is going into different inputs on my mixer, and right now they're all muted. So that's all pretty straightforward so far. Up here is the new part. So I've taken the output from each of these operators, and we're just going to think of these operators as having numbers. This first one is 1, 2, 3, and 4. And I've taken the outputs, and I've sent them into the inputs of this switch, 1, 2, 3, 4. And then the outputs of this switch, A, B, C, and D, are going out to the respective operators. A is going to 1, B is going to 2, C to 3, D to 4. And those outputs are going to the FM inputs on each of those operators. So now as we turn on the different switches in this matrix, in this switch module, we can send these different inputs to these different outputs. So we just click the little buttons to turn the switch on. And if you click them again, they actually go to negative. They go to invert the voltage, which is maybe handy for some people. I don't actually want that. So I'm going to right-click this and then go to inverting and disable that. So now these are all just on-off switches for me. That's better for our purposes for today. So now I've got this algorithm on the slide, a cascade or stack algorithm, and let's try to create this. First of all, it says at the bottom that operator 1 is going to be our carrier. So I'm going to unmute operator 1. Just got a sine wave there. And now it says operator 2 is modulating operator 1. So we're going to go up here and we're going to send operator 2 into operator 1. So we're going to go to 2 into A. So we find 2A, click that, and then as we bring up the depth on operator 1, we get some of those harmonics. Great. Now it says that operator 3 is modulating operator 2. So we're going to take the input from 3 and send it out into 2. So we're going to go to 3B. And now we'll bring up the depth on 2. And that gives us another layer of sidebands. Now it also says that 4 is modulating 3. So we're going to go over 4 and find the output to 3, which is going to be 4C. Turn that on and add some depth there. We don't need much before we get some harmonic sidebands there, inharmonic sidebands. And also at the very top, you can see that 4 has a little bit of feedback. So we're going to add some feedback here to operator 4. And so now we've got this setup where there are 3 operators all modulating each other, and then those are going into our carrier. So now let's turn some of these envelopes on and get some shaping. So I'll turn the level on my carrier on, and maybe the depth on my second 2 modules, and then maybe the feedback on my last module. And let's listen to this envelope now. All right, not a bad sound. Okay, let's try another algorithm, this time a branching one. So I've reset my patch. Now each of my operators are set to different frequency ratios. This time it's 1, 2, 2.77, and 5. So this branching algorithm, in this one, 4 is our carrier. So I'm going to unmute 4. That's the one that we're going to hear. And it says 2 and 3 are modulating 4. So I'm going to go up to first 2, and we want to send 2 out to 4. So that's 2D. We'll turn 2D on, bring up the depth there. And it also says that 3 is modulating 4. So we're going to send 3 out to 4. That's 3D. And we hear that one right away because my depth was already up. That's pretty inharmonic. Maybe we'll bring the level down on that one. Since the depth is already up, we can adjust the amount of operator 3 by using its level. And then it says that operator 1 has a little bit of feedback. So we'll go ahead and give it a little bit of feedback now. And then that operator is modulating 2 and 3. So we want to send 1 out 2. That's 1B. And then we want to send 1 into 3. That's going to be 1C. And we'll increase the depth on that. All right, so we've got a really rich inharmonic sound right now. Let's go ahead and add some envelopes to this. We'll add a level to operator 4. And then we'll do feedback on 1, and let's do depth on all the other ones. So now when I press a key, all right, so I've reset my patch, and let's try a third algorithm. This time I've reset my frequency ratios to 2, 4, 6, and 10. And so this is a root algorithm. This time we're going to have 3 carriers, 1, 2, and 3. So we're going to unmute 1, 2, and 3. And then we're just going to use 4 as a modulator for all 3. So we're going to send 4 to 1, that's 4A. Then we're going to send 4 to 2, 4B. Then 4 to 3, that's 4C. And then 4's got a little bit of feedback. Actually, I added a lot of feedback there. It didn't seem to get too noisy. Oh, there it goes. And now let's add some envelopes. So we'll do the level on each of our carriers. We'll do feedback on 4, and then we'll do depth on all of our carriers. It's kind of a nice plucky bell sound. All right, so I've reset my patch a third time. This time I've got my frequency ratio set to 0.5, 1, 2, and 3.1. So this last algorithm is going to be carrier only. So we're going to hear all of our sounds. So it's kind of an additive synthesis patch. We're just adding these sine waves together. We're not doing any FM modulation. But it says that carrier 3 has a little bit of feedback. So we'll add some feedback there to carrier 3. So it's got kind of an organy sound, at least before the feedback, which is common for these additive synthesis patches. We add that feedback, we lose that organy quality. And now let's go ahead and add some envelopes. So we'll add a level envelope to each of these, feedback to our third operator. And giving each operator a different envelope really helps us get away from that organy feel to a much different sound. All right, so let's just put a pin in all that, and now talk about the history of FM synthesis. So digital FM synthesis, in the way that we've been doing it today, taking what's essentially just vibrato, but speeding that vibrato up so it's so fast it's happening at audio rates, and then generating all these additional sidebands, and then having all this control over these different sidebands, That technique was first developed by John Chowning, an audio engineer and composer at Stanford University in 1971. And Chowning used that technique in a lot of his early works. In fact, in one in particular, Stria, which is on your listening assignment, Chowning uses these frequency modulation of these simple waveforms to create these really complex new timbres that slowly change and morph over time. He was actually inspired by a statue, this really elegant statue by Konstantin Brancusi called Bird in Space. It has this like feather-like shape. So he was really moved by that shape, and he sought to create kind of the sonic equivalent of the statue. And I think you can hear that in Stria as these shapes kind of move and bend in space with this elegant aerodynamicism. So listen for those kinds of shapes when you listen to the piece. So Chowning's FM technique was patented by Stanford University and then was licensed to Yamaha in 1973, and Yamaha used it to develop the DX7 synthesizer. Some of you may have heard of this. It's a really famous, historically significant synthesizer. It was the first commercially successful digital synthesizer. There were others before, like the Fairlight or the Synclavier. These were very, very large, very expensive systems, cost as much as an expensive car at the time, and were not very widely used as a result. But the DX7 was a lot smaller, more portable, more affordable, and as a result, it became one of the best-selling synthesizers of all time. It was a digital polyphonic synthesizer. It had 16-voice polyphony, and it had lots of preset patches that emulated all sorts of acoustic and electronic instruments, so things like electric basses, electric pianos, and then also things like flutes and harmonicas and things like that. It had a big interface that allowed you to do all sorts of programming, changing algorithms, changing envelope shapes, all the stuff that we've been doing today. But it was infamously difficult to program. You can see on the slide there's a tiny little LCD screen there in the middle, and you had to do all sorts of menu diving moving through that screen. And so very few people actually learned how to program their own timbres on the DX7. But its presets sounded so good that the presets themselves became widely used in all sorts of pop music throughout the 1980s. Almost every big pop hit in the 1980s had a DX7 on it. So I've listed some of those here on the slide. I'm not going to play them here, but I'll give you a link on Blackboard and in the description to a website that has a lot of great excerpts from these so you can focus and hear all those individual DX7 sounds. And there's a lot of different categories. You'll hear electric piano sounds, which are used a lot, like in this Whitney Houston song, digital slap bass sounds, which you can hear in that Aha song, also in like Kenny Loggins' Danger Zone, bell sounds, marimba sounds, a really interesting harmonica sound, which doesn't sound like a harmonica, but if you listen to that Tina Turner song, you'll probably recognize that harmonica sound. It was all over 80s and early 90s pop music. The only artist that I know of that really dived into the DX7 and really figured out how to program it and used it as a primary synthesizer in his compositional work was Brian Eno. Brian Eno used the DX7 in his Apollo soundtrack, which is a soundtrack to a film where he created a lot of ambient music, and he did it using the DX7 and actually dived into that menu and programmed a lot of his own patches and designed a lot of his own timbres. So the DX7 allowed users to choose from 32 different algorithms, and you can see those algorithms laid out on the slide there. Each algorithm consisted of 6 sine wave operators, and if you look through that chart, you can see how they're arranged in different branching or cascading or carrier-only formats. And if you look closely, you can see the feedback loops as well, and you'll notice that there's only one feedback loop per algorithm, which was the way the DX7 was set up, and that's kind of why I was using that as an example earlier. And the algorithms were displayed on the instrument's main panel. So if you look closely at that picture on the bottom left, you can see this layout with all the different algorithms being shown there. So it'd be nice if we had a way that we didn't have to use that switch module, we didn't have to use all those FM operators, but we can actually have something that was a little more self-contained, like the DX7, and it turns out that we do. There's a module called Dexter by Valley, which is a really complex 4-operator FM synthesizer. This is a really powerful synth. It's got tons and tons of options. I will admit it can be a little bit overwhelming at times. It's only got 4 operators, so it doesn't have as many as the DX7, but it's a lot easier to program than the DX7, but also has some wavetable functions, which I won't talk about today, but you can explore on your own. There's a video in the description and on Blackboard that goes over how wavetable synthesis works. So this is a really powerful synthesizer with lots of different options. All right, so here we are in Dexter, and I've got a patch already set up here. It might look a little overwhelming, but most of the stuff down here is just a way to get an interesting sequence. But let's focus on the main thing up here, which is Dexter itself. And let's first start by talking about its outputs. So it's got 7 different outputs. It's got AL and AR, operator 1, 2, 3, and 4, and then B out. So basically the way that Dexter works is it's got 2 different voices, voice A and voice B. So it's not polyphonic, but it does have a separate volts per octave input for voice A and voice B. So if you do what I've done here, I've set up a polyphonic MIDI input using 2 channels. I've sent that to a split module, and then I've sent my first channel to voice A and my second channel to voice B. And using all these outputs together, I can have two-voice polyphony, which is kind of handy. Let's go ahead and get rid of voice B for now. And I'm going to go ahead and set this back to monophonic. So voice B comes out the B output. That's pretty obvious. Voice A has a left and a right output. And that's because voice A, even though it's monophonic, you can use this chord option to choose from different intervals or chords. And if you choose different intervals, it'll send one note out the left channel and one note out the right. So I've got A, L, and AR coming down here to my mixer to a left channel and a right channel. So that's kind of handy if you want to send different notes different places. It also has major chords and dominant sevenths and things like that. If you just want to send a monophonic channel, when you're not using the right output, all the notes of the chord come out the left. So that gives you an option, which is useful. And then, of course, you've got 4 operators here, and each of them have their own individual output if you want to hear any operator individually. So the way that you can think of these different voices, voice A is effectively our carrier. Even though one of these operators is going to function as our carrier, voice A is kind of the way that our carrier exits Dexter. Voice B is kind of like a second copy of our carrier that we can detune. It's almost like VCO1 and VCO2 on the MS-20. So let's look at some of these master controls up here. On both of our voices, we have an octave knob. This just chooses different octaves, so this number is not a scale knob, it's just choosing an octave number. And then we've got a coarse tune and a fine tune. We've got the same thing on voice B, octave, coarse, fine. And then on voice A, we've got our chord selection and then a couple options for inverting and detuning those chords. I'm not going to go into that right now, but I'll post a link to an Omri Cohen video where he explains that stuff in more detail. So then here we've got an algorithm switch, and this is really great. As we switch from these different algorithms, we can see these different layouts show up on the interface there. And there's all kinds of algorithms, branched algorithms, cascading ones. The first 12 all come out A and B together. And then as we get higher than 12, we start to get ones where the carriers branch off and we send a couple operators out A and then a couple out of B. So you can see all these different setups that we've got there. You'll notice in all these algorithms that operator 4 is highlighted in orange because that's always the operator that's going to have feedback. So we've got this feedback knob that allows us to increase the feedback on that operator. And then this brightness knob is going to act as kind of a global level on all these different operators. But it doesn't actually come across as just a volume knob. It comes across as a way of increasing and decreasing sidebands, which is really useful. So let's go ahead and set up a patch and get some sound going. I'm going to disconnect this volts per octave from my keyboard and instead use this sequencer setup I've got down here. And this is pretty straightforward. I've got a clock controlling a Seek3 object. All 3 rows are going into this sequential switch along with a sample and hold, which is producing some random voltages. And then this first gate on my sequencer is randomly choosing between each of those 3 rows or the random set. And then all that is going through a VCA and a quantizer, which is set to a minor scale. And then we can send that to Dexter. Let's go ahead and send that to both A and B. So on each of our operators, we have a multiplier. This sets our harmonicity ratio. So right now it's 1. We can send it to whole number ratios. Then we've got a coarse tune and a fine tune. Here are wave and shape. These are two wave shaping parameters. So I'm not going to go into what these do right now, but I'll post some videos online that will explain that for you. This wave one chooses the wavetable position, and the shaper chooses how the wavetable, how the phaser moves through that wavetable. Then there's this level, which is just the volume for that particular operator. And then down here, there are CV inputs, actually multiple CV inputs for every one of these parameters up here. And they're color-coded, so the blue one controls tuning, purple wavetable, pink shaping, teal is volume, etc. Also, there's this settings button in the top left, which if you click in there, it gives you more options. It lets you choose what the wavetable is, how you want the different modulators to act, and things like that. So I'll let you guys explore that on your own. But now let's go ahead and set up some FM patches. So let's go ahead and set our operator tunings. I'll leave this one at 1. Let's set this one to 2. Let's set this one to 1/2. And maybe we'll give it a little bit of offset, some fine-tuning offset. And then we'll set this one to 7. And then let's go ahead and bring up the levels on each of these operators. So this one's already all the way up. Let's increase operator 2. So we're already getting a very bell-like FM sound. Let's increase operator 3. And then we'll do a tiny bit of operator 4. Doesn't take much. This is already a really bright timbre, so let's go ahead and bring down the brightness. That brings down the level of all of these together. All right, so one thing Dexter doesn't have is envelope generators. So these are kind of incomplete operators, but let's go ahead and add an envelope. So I'm gonna take an envelope and we'll go ahead and send that to, how about the overall brightness? And we need a way to trigger this envelope. So let's go ahead and grab it from our gate. And then as we increase the CV here, you hear that plucky aspect as our AD envelope shapes our brightness. And let's add another envelope to maybe shape the pitch. So let's send this to our third operator. We'll use it to adjust the pitch. And let's not do that on every note. So I'm just going to grab the first note of each 8-note sequence. And let's go ahead and increase. So you can see anytime that every 8 notes this envelope is struck, and that's going to affect the pitch of our third operator. And it's just a quick attack and a little bit of release. All right, and we've got an LFO here that we can send in as well. Let's go ahead and send that to maybe the level of our fourth operator. So we'll increase that. That's sounding kind of dubsteppy. Let's slow that down. So we've got some slow modulation on our fourth level there. And so this is kind of an interesting, kind of noisy timbre. And what's cool is we can just cycle through different algorithms and see how these same operators in a different arrangement would sound. The timbre doesn't change dramatically with each one, but it does change. This one's a little rounder. Oh, this one almost sounds like a bass guitar. Now you can hear where some of those DX7 bass sounds come from. Nice organ sound. So yeah, you can explore all these different ones. You can also change the fine tuning on our second oscillator. That can actually make things sound a little fatter. Maybe on a different algorithm. This is without fine tuning. This is with it. And let's maybe do something polyphonic now. So I'm going to choose an algorithm where there are two different outputs. Yeah, let's go with this one. And I'm going to break off my sample and hold here and send that to a separate VCA. We'll set this to a 3 switch. So this is only going to cycle through my 3 rows now. And my sample and hold is going to a separate VCA. We'll send that also into my quantizer here. And we'll send the volts per octave to B from that sample and hold. And let's bring B up a little bit. And so now you can hear some polyphony. I've got my sequences here, but then also my random sample and hold voltage. They're each going into different inputs, different voices, and so now I get this nice polyphonic texture. All right, so I know that was a lot today. Thank you for your patience with all this. But I think this is really important stuff for us to learn, and this is a good opportunity working in DCB Rack to do that. So just to review, today we talked about harmonicity and audio rate modulation. We spent most of the period on FM synthesis. We talked about the theory and patching of FM synthesis, looked at things like sidebands, modulation index, feedback, and operators. We spent some time with the Bog Audio FM operator module. Then we looked at creating some different algorithms, first using the switch module. Then we talked about the history of FM synthesis, talked about John Chowning and the Yamaha DX7, and then we ended by talking about Valley's Dexter module. So there's a lot more to explore in Dexter. There's some videos online that will help you do that if you're interested. But yeah, moving forward, we're just going to be talking about the final project, which will be due at the very end of the semester. So I'll post some guidelines for that coming up here in the next few days.